Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. Up to this point, we've learned lots of trigonometric formulas and relationships, like reciprocal, quotient, and Pythagorean identities. But now comes one of the most creative parts of trigonometry, proving identities. This is where we don't just solve for a variable. We show that two expressions are always equal for every single angle that makes sense. Before we jump in, here are some key reminders for proofs. We want to work on only one side, and it's usually going to be the side that looks a little bit more complicated. We can use all the tools at our disposal, which up to now, we have reciprocal, quotient, and Pythagorean identities. And if you ever get stuck, you can always replace everything in terms of sine and cosine. And lastly, don't multiply across the equal sign because we're not actually solving for anything here. We're showing equivalence. And you'll notice that we're going to be using something that looks like the equal sign, but is not. It actually has 3 parallel bars instead of 2. And now some key tips for proofs. If you see complex fractions, you can simplify it by multiplying through by common denominators. And if you see a binomial, you can multiply by the conjugate to create nice patterns for simplification. So let's take a look at how all of this works through an example. For this example, we're going to be working with the left side because that's the side that looks a little bit more complicated. So we get secant x times sine x plus cos x is equal to, and now we can go ahead and use our quotient rule to replace secant x with 1 over cosine x. And we're multiplying that by sine x plus cos x. And this is equal to, we can distribute it, and we get sine x over cosine x plus cos x over cos x. And now we know that sine x over cos x is equal to tangent x, and cos x over cos x is just equal to 1. So we end up with tan x plus 1, which is our right-hand side. So thus, we have proven this identity. Let's move on to our second example. Again, we're going to be working with the left side here because that's the more complicated looking side. So we start with 1 plus sine squared x minus cos squared x over 2. And now I am just going to reorganize this a little bit. So this is going to be 1 minus cos squared x plus sine squared x. So I'm writing this out so that you can see this clearly. We can use our Pythagorean identities here because that says sine squared x plus cos squared x is equal to 1. So if we subtract cos squared x on both sides, we get sine squared x is equal to 1 minus cos squared x. So therefore, we can go ahead and replace this 1 minus cos squared x with sine squared x. So then we get this is equal to sine squared x plus sine squared x over 2, which means this is going to be 2 sine squared x over 2. So this simplifies to just sine squared x. And that is exactly the right-hand side. So again, we have proven this identity. For our third example, both sides look equally complicated. You can pick either side here, but we're going to pick the left-hand side. So we start with 1 minus sine x over cosine x. So this is the binomial that we were talking about earlier. So what we're going to do is we're going to multiply the top and bottom by the conjugate, which means we're going to take our 1 minus sine x over cos x and multiply it by 1 plus sine x over 1 plus sine x. So notice this is not cross multiplying. We're not multiplying this 1 plus sine x from the right side over to the left side. What we're doing is we're taking this entire left side expression and multiplying both the numerator and the denominator by 1 plus sine x. So then this is equal to, our numerator is now just going to be a difference of squares. So that'll be 1 minus sine squared x. And then our denominator, we're actually going to leave as is. We're not going to distribute our cos x. So this is going to be cos x times 1 plus sine x. And again, we can go ahead and use our Pythagorean identity because 1 minus sine squared x is just equal to cos squared x. So this will be cos squared x over cos x times 1 plus sine x. And now one of the cosine on the numerator is going to cancel out with the cosine x on the denominator. So then we end up with cos x on top. And then on the bottom, we just have 1 plus sine x. And that is the right-hand side that we're trying to prove. So now we have proved this identity as well. And now for our last example, we have something that looks quite complicated. So here we can see that the left-hand side is more complicated looking than the right-hand side. So that's the side we're going to start with. So we have 1 over 1 minus sine x minus 1 over 1 plus sine x. And then this is all over cos x. So right now, this looks pretty gross with fractions within a fraction. So let's go ahead and try to simplify that. And what we're going to do is we're going to multiply this fraction by both of the denominators that you see in the numerator. So we're going to multiply this by 1 minus sine x times 1 plus sine x. And then we need to do that with the denominator as well. So 1 minus sine x, 1 plus sine x. So then this is equal to, so if we take this and multiply it to each of the fraction on top, for the first one, the 1 minus sine x is going to cancel out. So we're left with 1 plus sine x. And then with the second fraction, the 1 plus sine x is going to cancel out. So we're going to be left with 1 minus sine x. And then as for the denominator, if we have 1 plus sine x times 1 minus sine x, that's just 1 minus sine squared x, right? Because this is equal to 1 minus sine squared x because it's difference of squares. But we know that that is equal to cos squared x. So that means our denominator is going to be cos x times cos squared x. So we get this is cos cubed x. And now we can go ahead and combine like terms on top. So we get 1 minus 1, so the 1 will cancel, and then we get sine x minus negative sine x. So we get 2 sine x on the top. And then our denominator is still cos cubed x. Now comparing what we have to what we want is what's on the right-hand side. So we have that 2, and then we can see that we have a secant squared x and a tan x. So that tells us we should use our quotient identities here to simplify this. So this is equal to 2, and you can think of this as if you had sine x over cos x, and then we have 2 extra left over cos x, or cos squared x, on the bottom. So then this is equal to 2 times, now sine x over cos x is our tangent x, and then 1 over cos squared x is going to be our secant squared x. And now we have arrived at the right-hand side and have thus proven this identity. And now let's do a quick recap of everything that we covered in this video. We saw how replacing everything with sine and cosine when we're stuck helps us simplify the expression. We used the Pythagorean identities multiple times to simplify terms like sine squared x and cos squared x. And when dealing with tricky denominators, we multiplied through by the conjugates to remove them. And finally, when dealing with complex fractions, you can simplify inside out to get rid of them. And now it is your turn to give this a try. Can you prove this identity on the screen here? Make sure to leave your answer in the comments below and let us know if you'd like to see more content on proving trig identities in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.